I will try to stay in time.
No worries.
20 minutes, yes. I
20,
will try,
20,
yes.
25 minutes. Yes.
Okay, that's fine.
So, hello everyone. We are here for another Synergies talk in this series. Today, we are very much delighted to have our lovely Katia Biazzo. She's a researcher at the Observatory of Rome, and she's mainly an expert in star formation and the early evolution of the young stellar populations. She's also extremely focused on the environmental impact of the formation, specifically disk accretion rates and also metallicity. And to the best of my knowledge, she is also very much interested in disk and star formation studies. So today we will see an amalgam of all of these like investigations that she has done, and we're very much looking forward to this interesting, great talk. Katia, please take it away. The floor is yours.
Yes. Thank you, Fatima. Thank you, Julia, for the talk. And okay, I will talk about distant clusters, young distant clusters, and this is a brief outline of my talk. I will briefly introduce the context and the motivations for studying distant clusters. I will talk about very briefly, I will try to be brief about the work done till, let's say, in the last 15 years in the context of the accretion disk fraction of distant clusters in the local group. And then I will introduce some recent results in which I'm involved, and both from the space and from the ground, and future perspectives with new instruments. Okay, one of the aims to study in the study of young clusters is not only to understand how accretion properties are dependent on stellar properties like mass and ages, but also how environmental conditions may affect the accretion process, disk dispersal, and in general planet formation, because protoplanetary disks are the planet birthplace. From we know from we have that from one side, most of the regions studied so far are nearby and with solar metallicity. Several methods were applied to try to find the best combination for the, in particular for spectroscopy, to find accurate accretion rate determinations, and this was done for many targets per star forming region, for many star forming region in the solar neighborhood. But at the same time, we have that many stars formed in the universe at around in the universe at around redshift 2, when the star formation rate density had a peak in the so-called cosmic noon, and when the metallicity was very close to the one, let's say, present in Magellanic Clouds, in particular the small Magellanic Clouds. Therefore, studying star-forming regions with metallicity around 0.2, 0.3, the solar metallicity, is like to study the, let's say, the early universe. I mean, early after then around 3-4 giga years from the Big Bang. But till a few years ago, spectroscopy in distant clusters was difficult or hampered because of crowding. Therefore, photometric methods were applied to derive accretion properties. But now, thanks to JWST and not only, in the future much better, spectroscopy start to be possible even for low mass young stellar objects, because in this talk I will mainly talk about low mass stars. This is, I will give you a brief introduction on the photometric method applied in the last, let's say, 15 years to derive accretion properties, in particular the combination of broadband visible and near-infrared band together with narrowband H-alpha photometry allowed us to derive, to catch the emission in H-alpha of targets due to accretion. And in particular, this kind of method was applied to different regions, both in the outer galaxy and in the small and large Magellanic Clouds. And one of the result was that it was found that in these clusters with low metallicity, we found accretors even at 25 megayears, more or less. And also evidence of multiple population was present, younger accretors and older accretors. Therefore, it was clear that accretion was a matter, of course, of age, but not only. It was also a matter of mass, because looking at the relationship with age and masses, some trend appeared. In particular, mass accretion rate were found higher for younger objects, like in the left panel. And looking at the right panel, I mean the M-ACM star relationships, the slope of this relationship changes according to the age, being smaller for younger ages and close in slope as those in the nearby star-forming regions. And but not only in this cluster, it was found that also accretion was a matter of metallicity, because in one of the results it was that the accretion of these young stellar objects were found, higher, at a higher level than the solar metallicity regions. And but in particular, it was found that mass accretion decreased more slowly with time at lower metallicity than solar one. And also dependence on the density was present. In particular, mass accretion was found higher for higher values of surface density. And also, one of the other evidence was this work, which were mainly led through HST photometry, was the following one. If we look at the distribution, the position of this target in the space, in the sky, we saw that younger stars are more accreting targets were found to be more clumped, more concentrated than the older one and less accreting targets. And okay, this is this was the main result I would like to show concerning the accretion properties in the past. But what about disk fraction? This is one of the main paper in which was claimed that in the low metallicity region, lower disk fraction was found. And in particular, this author, Yasui et al., found a disk dispersal, faster disk dispersal, let's say, in low metallicity regions, let's say within 1 mega year. But recently, Patre et al. Found a slightly different behavior. I mean, they found again lower diffraction for lower metallicity regions, but they do not find any evidence of faster decay in subsolar metallicity regions. And they also found a correlation between disk fraction and metallicity for two groups of ages. The authors claim that one of the main reasons on contradictory results is mainly due to the determination of the stellar properties, because, for instance, the same clusters previously analyzed by the Yasui et al. And then analyzed by these authors now appear to be older than previously. This is why they do not find correlation, they do not find faster decay in subsolar metallicity regions. But also, one of the the claim by the author was also that different diagnostics may lead to different results. In particular, this was also confirmed very recently by the same Yasui et al., who, for instance, obtained disk fraction from long wavelength diagnostics with JWST, finding for the same clusters previously analyzed by them very higher value in disk fraction. And also the same clusters analyzed by Patra in J, H and K, analyzed previously in longer wavelength by Mario Guarcello et al., the disk fraction was higher. Therefore, this could be one of the reasons is that we trace different regions of the disk, inner disk versus smaller wavelength versus outer disk at longer wavelength. And also, another issue is related to the possibility that we have, when we deal with disk fraction, different author may trace different spatial scales, and in particular, a dependence on density, surface density is also present. In particular, increasing the surface density led to a decrease in disk fraction. And this is also was previously derived by Mario Guarcello, again, who obtained the disk fraction decrease with surface density. And also the same authors found a very strong dependence on the disk fraction on the photoevaporation due to UV radiation. This is only to show that when we deal with this kind of cluster, this is, for instance, one of the closest massive Young association. Therefore, when we deal with these extreme environments, extreme both in radiation, in metallicity, in surface density, we have to consider all the feedback mechanisms which may deal to disk erosion or lower or higher values of accretion rates. Now, I would like to show you results obtained. This is the GTO program with JWST, and then from the ground. This GTO program started a few years ago at cycle 1, and the main aim is to, we observed 3 main clusters, young clusters with different characteristics in different places of outer galaxy, large Magellanic Cloud and smaller Magellanic Cloud with different metallicity and different distances. And the main aims is to investigate accretion properties at different metallicity, extinction properties in dense environments, and also to look at the nature of dust in these in low metallicity regions. Now I'm going to show you first result on the third cluster on the right, the one with the lowest metallicity, around 1/8 the solar metallicity, in the small Magellanic Cloud, NGC 346. This is the first result, in particular from color and color magnitude diagrams obtained with many filters, because this cluster was observed with NIRCam, MIRI, and also NIRSpec, and NIRCam with many filters. And from the combination of different color and color magnitude diagram, here I show only one example, we find many targets, very young very young targets and accretors, and we both Paschen alpha and Bragg alpha emission. And if we look at the distribution of these targets in orange and in violet on the right panel, the spatial distribution, they are mainly concentrated along the main molecular filaments where the dust is present, because this panel show it is obtained with a filter where the polycycle aromatic hydrocarbon emission is present. So therefore, we are mainly looking at the dust distribution. And part of these young targets were observed with NIRSpec, and some of them were published 2 years ago. In particular, we published the first 10 targets with around solar masses, only to confirm how the previous result we obtained with HST from the same cluster, because the targets were selected from the previous HST photometry. And now with JWST, they show even with a wide range of ages, let's say within 20 megayears, they show emission of diagnostics which are typical of accretors. I mean, Paschen alpha, bracket gamma, and bracket beta, for instance, and also emission in the near infrared, like shown on the right panel. But not only, we also observed, in particular in the intermediate mass targets, ICES of water, CO2, and CO. And this is the first detection beyond the Milky Way of ICES in intermediate mass targets, because previously previous results beyond the Milky Way were obtained for high mass target. And therefore, in this kind of cluster, we detected which are very poor in metals. We detected accretors, dust, and ices. Okay, now I would like to show you this recent result, which is this is a paper which is under review, and in particular, this is a cluster observed from the ground with moths at the Large Binocular Telescope. This cluster sharp 284 is a cluster at around 5 kiloparsec from us, and with a metallicity of 0.3, 0.5 solar metallicity. We selected the targets from the main catalog by Mario Guarcello of disk pairing objects. In particular, we combined two mass Spitzer and IFAS photometry to obtain in the end a total of 90 targets. In the end, around 70 were observed with and on the right panel I show you the spatial distribution in the 9 pointings, most pointings of modes, and other pointings in long slit. And this is an example of one of the strongest accretors in this cluster. This is a metal pool cluster in which we observe almost all the diagnostics in both the blue and red grid of the instrument, accretor diagnostics and emission. And okay, here we selected for the 70 targets 9 diagnostics in 3 Balmer lines, 3 Paschen lines, and 3 calcium 2 infrared triplet line, and derived line luminosity and therefore accretion luminosity. In this panel, I show you the accretion luminosity as a function of stellar luminosity, and in particular, it is clear how compared to other clusters, both in our galaxy, in nearby, like Lupus, and the outer galaxy like NGC 3603 or Small Magellanic Clouds, the one I showed before, and we see how at a given stellar mass we find the same region in accretion luminosity for these stars in yellow, for our stars in yellow, as those found in nearby regions. And the other result I would like to show is this one, in particular the mass accretion rate as a function of mass, in the upper panel as a function of age. We find in yellow our targets, while several colors are associated with different clusters in different regions in the nearby, gray and green. The same cluster analyzed by us was also part of the targets were previously analyzed by other authors, here in pink and in red, using only the H-alpha line. And then other clusters analyzed through JWST data, in particular the one in blue for cluster solar metallicity clusters of the outer galaxy, and in green, in black, the small Magellanic Cloud targets. We see how for this low metallicity region in yellow we find high values in mass accretion rate, and in particular higher mass accretion rate for younger targets as normally observed in other clusters. We find that given mass spread in mass accretion rate of around 1-2 dex, as observed in nearby regions, and which is not associated with variability, because we have also analyzed variability for our targets, because we have obtained for some targets also multiple observations. And one of the main results is that with these statistics, at least we do not see any significant evidence of offset with respect to, in terms of mass accretion rate, in terms of solar metallicity, in terms of compared to solar metallicity regions. Therefore, we plan to perform systematic studies, because one of the main issue is that we have very, very pure statistic for this kind of class. We have few targets per cluster and very few targets analyzed in this way. So systematic studies are needed for this kind of clusters. And here I would like to, these are my main take-home messages, only to show that we have different results. I mean, we have contradictory results or partially contradictory results in this kind of cluster, because we see high accretion level at low metallicity, but also lower disk fraction. So they could seem to be contradictory result, but maybe possible reasons can be due to the possibility that this kind of low metallicity regions imply lower disk temperature, which means lower lower opacity, lower viscosity, which maybe result in longer time scale of accretion, but also the weaker effect of radiation pressure in this kind of low metallicity regions could strengthen this accretion in rate and duration. But also we have biases, because different proxies may lead to different or partially different results. So one of the main steps to be done in this field is to obtain a systematic study to look at the dependence on accretion and also diffraction on environmental conditions. And here I would like to show you future instruments that, in my knowledge, are the one which are which have a working group or science cases looking at the low metallicity environments, both in the outer galaxy and the Magellanic Clouds. And in particular, the moons will start soon. This multi-object spectrograph, but in the future, multi-conjugate or IFU instruments or multi-IFU, like in the case of SHARP, will be very useful in this field. And in particular, concerning the possibility to have a higher level of statistics, WST will give us a really step forward, because within WST WST, in particular within the galactic WG, there is a sub-WG on star formation, which is led by Germano Sacco and Carlo Manara, in which in the end, we will be able to observe millions of young stars across the Milky Way and the Magellanic Clouds, not only to investigate the mechanisms driving star formation rate across the Milky Way and beyond, looking at the dynamical evolution of massive clusters and the rule of feedback, and also the time variability will be observed with WST. But one of the aim of this working group will be to have, in the end, the largest survey of low metallicity young stars. And in particular, here I show you the field of view of WST in the lower panel, and how a typical cluster of the outer galaxy, like the one I showed you before, will appear as a field of view. This is only to show how with WST we will be able to cover for such a kind of typical cluster in the outer galaxy. With the IFS, the most of the inner part of the cluster, the young cluster, which will be important because with only one exposure, we will be able to catch the most of the inner part, and therefore hundreds of young stars which actually are crowded and cannot be observed. While the possibility of moss in the other part of the cluster, in particular also in the outer part, outer than the main cluster, will give us important information for the feedback, because the feedback here will be lower than the one in the inner part of the cluster, and this will be important to have, let's say, a benchmark for the comparison with the inner part of the cluster. And that's it. I try to stay in time.
Well, thank you so much. This is amazing talk, like always.
Thanks.